All right, welcome to the first screencast for the Unit 3, Structure and Properties of Ionic and Covalent Compounds. So in this unit, we're going to learn all about, obviously, ionic and covalent compounds, what they are, what their properties are, how to write formulas for them, how to name them. So we're going to do nomenclature. And we're also going to talk about their structures. So we're going to do a lot with not just Lewis dot diagrams, but Lewis structures, and learning specifically with covalent compounds. So our first essential question, how are Bohr models constructed using valence electrons? So this is a nice review of what we did last unit, but kind of tying everything together. Because things bond because of valence electrons, so we have to review that a little bit. So chemical bonding, what is a chemical bond? It's the force of attraction between any two atoms in a compound. So for some reason, those two atoms are attracted to each other. It could be because of an opposite charge, so a positive and a negative charge like in an ionic compound, or it could be because they're sharing electrons to try to get full. Because remember, the goal is when they form a chemical bond is to get full, to have 8 valence electrons. So interactions involving the valence electrons are responsible for the chemical bond. So when we're talking about things reacting, we're not talking about all of the electrons in an atom. We're specifically talking about the valence electrons, which is why it's so important to know the number of valence electrons and then therefore the oxidation numbers that everything forms. So a little bit on Lewis symbols or Lewis dot structures. This should be a review for you. A Lewis symbol is just a way to represent the atoms using the element symbol and then valence electrons as dots. So instead of actually drawing a Bohr model, we just draw the outermost energy level, and 1 dot equals 1 electron. So when you're writing a Lewis symbol, you place 1 dot on each side until there are 4 dots around the symbol. Because remember, with the Pauli exclusion principle, they don't pair up until they're all full. So you've got to have 1 on each side, and then you can start pairing them up. So that's the second rule. Then you add a second dot to each side in turn. The number of valence electrons limits the number of dots placed. So if something only has 1 valence electron, it's only going to have 1 dot. If something has 4 valence electrons, it's going to have 4 dots going around it. Think of a box around it, around the element symbol. And then each unpaired dot is an unpaired valence electron. That's where they can form a chemical bond. That's where they're not full. They're not happy. So if you look here, everything in the first column only has 1 dot. Well, it's much easier for them to lose that 1 than it is to gain 7. So that's why they lose the electron. These all have 2 dots. We'll talk about the transition metals in a little bit. We're going to deal with those in this unit because they don't follow the rules. Everything in this column has 3 dots. So you can see the 3 valence electrons. Everything here has 4. These guys have 5, but you can see how there are unpaired electrons. And where they're unpaired at, this is where they're ready to bond. So we've got unpaired here for the oxygen group having 6, the halogens having 7, and then the noble gases are full with 8. So you can see all sides are filled with the 8 electrons. Wherever you see anything unpaired, that's where they can bond. So they're not going to bond here, they're going to bond where they are unpaired. So we're going to do some practice in class with this. The cool thing is this looks like a Bohr model. This is just the outer energy level of a Bohr model. So instead of showing all of the electrons, you're only showing the valence electrons. So instead of having a circle around magnesium and showing those 2 in the first one, and then for magnesium showing these 8 in the second one, and then these 2 in the third energy level, you're only showing the outermost energy level. But again, 2 electrons in the first energy level in your first circle, 8 in the next energy levels, and each orbit or each energy level matches the periodic table, so you can have up to 7 rings around the outside of an atom. So Bohr models, Lewis dot structures show you the same thing. Bohr model gives you a little bit more information because it shows you what actual orbit they're in, but you would know that these are in the 4th orbit because they're in the 4th row. These are in the 3rd orbit because they're in the 3rd row. So just by knowing their location, you don't necessarily have to draw a Bohr model all the time. So we're going to do some practice with that in class as well. Okay, so our kind of next section here, so that's just a little bit of review of valence electrons. How are bond types predicted using electronegativity values? And what are the primary differences between an ionic and a covalent bond? So these are also the essential questions that need to go at the top. I know we have 3 essential questions for one kind of note sheet, but we're covering all of this stuff at once. So remember talking about electronegativity with the periodic trends? Well, I told you that was going to come back. It's coming back right now. Okay, so principal types of chemical bonds. There are 2 types of chemical bonds. The first one is called an ionic bond. When you hear ionic bond, you need to think ions. When you hear ions, you need to think charges. So in an ionic bond, the attractive force is due to the transfer of 1 or more electrons from one atom to another. So something loses and something gains. Generally, we associate this with a metal and a nonmetal. The metal loses and forms a positive ion, and the nonmetal gains and forms a negative ion, and then they're attracted to each other. That opposite charge attracts them to each other, and they form a chemical bond. In a covalent bond, the attractive force is due to sharing of electrons. We associate this with nonmetals. Nonmetals all want to gain. So when you look at a nonmetal, it does not want to lose electrons at all. It wants to gain. So 2 nonmetals can come together if they both decide, okay, we'll share these electrons. So a little bit about ionic bonding. Electrons are lost by a metal and they are gained by a nonmetal. So each atom is trying to achieve a noble gas configuration, which if you remember, if I go back here to this periodic table, these guys right here only have 1 valence electron, so it's easier for them to lose 1. And if they lose 1, like sodium loses 1, then it's going to lose this whole 3rd energy level, and it's going to now look like neon in terms of its electrons. That's the goal. Everything wants to look like a noble gas, so it's going to try to gain or lose to get to be a noble gas. And then so you have 2 ions that are formed, a cation and an anion. The cation is positive, the anion is negative, or the cation is the metal and the anion is the nonmetal, and then they're attracted to each other. And that's what creates the ionic bond. So this next slide is going to kind of take you through an example of this. So sodium plus chlorine yields sodium chloride. Sodium has a very low ionization energy because it really wants to lose that 1 valence electron. So it's going to lose it and form a positive ion. And now there's this free electron. That free electron is available to go to chlorine, which has a very high electron affinity, meaning it wants electrons. So chlorine is going to take in that electron. And if you see, chlorine on its Lewis dot structure is missing 1. So now chlorine is going to take it and form a negative ion. And when they bond together, you get this attraction. As a sodium atom loses 1 electron, it becomes smaller. The chlorine becomes bigger because it gains 1. And the attraction of the sodium cation with the chlorine anion forms sodium chloride. So they bond together in this kind of crystal lattice formation where you have a chlorine bonded to a sodium, bonded to a chlorine, bonded to a sodium into this crystal. And that's what makes the salt that we see. In covalent bonding, let's just look at this example right here. Let's look at hydrogen. Hydrogen doesn't exist by itself. It exists as H2 because each hydrogen needs an electron. It has 1 electron in its valence shell, so it needs 1 more to be full. So both hydrogen atoms have an equal tendency to gain or lose electrons. So because they'll both do the same thing, when they bond together, they're going to share. So if hydrogen has 1 extra, this hydrogen has 1 extra, they can just share that pair of electrons between the 2 of them. And that forms a covalent bond. So each atom attains a noble gas configuration by sharing the electrons. So they would both get to there. For hydrogen, they only need 2. So it gets to 2, and this hydrogen gets to 2, and they're both happy. So each hydrogen now has 2 electrons around it. And this is what we call a covalent bond when they share. So a little bit more about covalent bonds. Covalent bonds form between atoms with similar tendencies to gain or lose electrons. We associate covalent bonds with our nonmetals because they both want to gain, or they both could lose, but they both want to gain with the same tendency. So we generally see covalent compounds forming with them. Compounds containing covalent bonds are called covalent compounds, or molecules. That's probably the more common term used for them. The diatomic elements, we'll talk about those when we do chemical reactions, but the diatomic elements, these are 7 elements that are not happy by themselves. So that's why they always exist in nature in pairs. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Ironically enough, they form a 7 on the periodic table, and we'll label those later. But they all form covalent compounds. And here's a few more examples of covalent compounds. So if I have hydrogen with 1 valence electron, and oxygen has 6, so it is short 2 valence electrons. Well, if this one hydrogen that needs 1 more electron, and this oxygen right here, it needs another one in that spot. So if they share there, they're happy. But oxygen has to share with 2 hydrogens because it's short 2 electrons. So if they share among these spots, then they both become happy. Or for like methane, here is carbon only has 4 valence electrons, so it needs 4 more. So it's going to have to share along 4 spots, which is why it forms a bond with 4 different hydrogens. So now if you look around hydrogen, for its valence shell, it has 2 valence electrons. Each one has 2 valence electrons going around it. And carbon now has 8, making it full, but they're sharing those pairs. And that's all that's describing. So the cool thing about covalent compounds is, yes, the electrons are shared, but they might not always be shared evenly. So ionic bonds, remember, involve the complete transfer, whereas covalent bonds involve the sharing. You can have a polar or a nonpolar covalent bond. A polar covalent bond is where they're going to share unequally. Like if the hydrogen and the oxygen and water are sharing the electrons. The oxygen does not share this pair 50-50. The oxygen shares unevenly, and that makes it polar. So in this case, hydrogen combining with fluorine, so it's going to share this pair to make everybody happy, but fluorine takes the electrons a little bit more. It's more electronegative. It's stronger. It has more pull. So that leaves the hydrogen somewhat positive, and the fluorine is now somewhat negative, which is why you might see like a slightly positive, slightly negative. These 2 electrons are not shared equally. Fluorine pulls them a little closer to itself. And when it does that, you'll see sometimes we'll write this slightly negative and slightly positive because it's not a true positive or a true negative. So it's kind of this, fancy cursive S to show that it is unevenly shared, and this creates a polar molecule. So it's going to have slightly uneven charges, which gives it all sorts of weird or cool properties. So electronegativity is a measure of the ability of an atom to attract electrons in a chemical bond. So in order to measure electronegativity, you have to form a chemical bond, so noble gases are out. And elements with the highest electronegativity will have a greater ability to pull the electrons towards themselves. So the higher your value, the more electron hungry you are. So when you form a bond, if you have a higher value, you're not going to share evenly. So if we look at this periodic table of values, remember electronegativity goes down as we go down the periodic table, and it increases as we go across. So fluorine has the highest electronegativity value of 4, and francium down here has the weakest of 0.7. So you can tell what type of a bond things are going to form by the differences between them. So if chlorine and oxygen bonded together, or if chlorine and nitrogen bonded together, that would be a nonpolar bond because there's no difference in the value. But if fluorine and chlorine bonded together, there is a difference in value, so there's going to be some uneven sharing. And the cool thing is you can just look at the difference between the elements, and you can tell what type of a bond is going to form. Okay, so I'm real quick going to go through this slide just to make sure we have enough time. Which would be more polar, HF or HCl? Well, if you look at the difference, 4 minus 2.1 is 1.9, 3 minus 2.1 is 0.9, so this one is more polar. So if you look at these values right here down at the bottom, and we're going to do this in an activity, but if you look at these values, the difference If it's 1.7, 0.3 to 1.7, or 0 to 0.3, it tells you what type of bond forms.